Hello everyone, this is Dr. Lennon, and I would like to talk about some of the trig identities today, and um, let's jump right in. So let's start with a family of identities known as the Pythagorean identities. So basically, since the unit circle is defined by the equation x squared plus y squared equals 1, and we have the correspondence associating to any point on the unit circle where angle theta intersects that unit circle. That point would have coordinates cosine of theta comma sine of theta. Basically, in the equation for the circle x squared plus y squared, you can replace cosine of theta and sine of theta. So the first of these Pythagorean identities is cosine squared theta plus sine squared theta is equal to 1. So just one little note on the notation. So note that for shorthand, cosine squared theta means cosine of theta in parentheses quantity squared, so cosine of theta times cosine of theta, and not cosine of theta squared. So do not confuse those two things. Cosine squared theta, where the squared symbol is written between the cosine and the theta, means that the cosine itself is actually squared. Using the other reciprocal identities, so recall we have some reciprocal identities, or the reciprocal trig functions. And those are the secant, cosecant, and tangent. So the secant of theta, the cosecant of theta, and the cotangent of theta. So the secant of theta is the reciprocal of the cosine, so secant of theta is 1 over the cosine of theta. The cosecant is 1 over the sine of theta, and the cotangent is 1 over the tangent of theta. So there are two other versions of the above trig identity, the Pythagorean identity. So there are two other versions of, let's just write down. A lot of times when they do this identity, we'll write it as sine squared theta plus cosine squared theta equals 1. Again, addition is commutative, so you could write it as cosine squared plus sine squared, or vice versa. I feel like I see it written as sine squared plus cosine squared more often, even though cosine technically represents the x coordinate. So let's call it number 2. 1 plus tangent squared theta is equal to the secant squared theta, and the third version of the identity is cotangent squared theta plus 1 is equal to cosecant squared theta. So it appears the way that I've written them, these identities, it'll be easier to start with the other ordering. Of course, these things are all the same, but what do I mean? So I want to write down a proof of these facts. So let me write this down using the previous ordering. So cosine squared theta plus sine squared theta. And let's just, as an exercise, show that number 2 and number 3 are in fact alternative versions of number 1. So what I'll do is I'll show you number 1 or number 2, and you can do number 2 at home. Try and see if you can verify that yourself. It's not so difficult. So if we start with cosine squared plus cosine squared theta plus sine squared theta, equals 1. That's all we have to do is divide both sides. So what are we trying to get to? We're trying to get to number 2, which is 1 plus the tangent squared theta is equal to cosine squared theta. So let's divide on both sides by the cosine squared of theta. So now we can use the common denominator to write this as cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta equals 1 over cosine squared theta. So we just divided both sides by cosine squared theta. So now we can perform a little simplification. So cosine squared theta over cosine squared theta is the same thing, and then we can actually rewrite this as sine of theta over cosine of theta, quantity squared, appealing to some laws of exponents, and similarly the right hand side of the equation can be rewritten as 1 over cosine theta quantity squared. Well, now what we can do is we can replace those with the usual trig definitions that we've just seen above. Sine of theta over cosine of theta is the tangent of theta. So this is actually tangent squared of theta, and the right hand side 1 over cosine is the secant, so this is just secant squared theta. And that completes the proof of number 2. So number 3, so I'll just say you try this. Again, it's very similar. That's all you really have to do is go ahead and, rather than divide both sides of the equation by cosine squared theta, you want to divide both sides by sine squared theta and simplify. Okay, so there are some other identities that come up. Some of these, the two very important ones, are the angle sum formulas. Now, I'm just going to do them for sine and cosine. There are angle sum formulas out there for the other trig functions, but they all kind of come from these, and these are the ones that are encountered most frequently. There's a variety of ways to prove them. We won't be going over the proofs here, but you can see the proofs are often given geometrically, so you can appeal to a geometric argument if you want to look into that. Okay, so if we have two angles alpha and beta and we want to break apart the sine of alpha plus beta, how can that be accomplished? Well, it turns out that this identity can be rewritten as sine of alpha cosine beta plus cosine alpha sine beta. A lot of times people will omit the parentheses here. Sometimes I do it if I just want to specify explicitly what the argument of each trig function is. And then from this, as a special case to each of the angle sum formulas, you also have what's known as a double angle formula. So the double angle formula is, imagine alpha and beta were both the same value. Let's call them the same letter. Let's suppose it were theta. Well, then what would we have? On the left-hand side, you would have theta plus theta. So the double angle formula for sine is a corollary. So theta plus theta would be 2 theta. So on the left, we would have sine of 2 theta. And then on the right-hand side, again, alpha and beta are the same, so we'd have sine theta times cosine theta plus the second term would also be sine theta times cosine theta. So this would actually just be 2 copies of sine theta cosine theta. So that's the double angle formula for sine that you can think of as a special case of the angle sum formula for sine. So what is the angle sum formula for cosine? So this is cosine alpha plus beta, and cosine is cosine alpha times cosine beta minus sine alpha times sine beta. And again, we're going to have a double angle formula for cosine if we allow alpha and beta to both be the same value. Again, we'll just call it theta for the double angle formula. So double angle formula for cosine. So this is given, we would have the cosine of 2 theta. That would equal cosine theta times cosine theta, which is cosine squared theta, and then minus the sine squared theta. So those are your double angle formulas. So when you're solving trig identities, one of the big tricks is often combining these 2 double angle formulas in some fashion with the Pythagorean identity. So let's just note that. So note that the double angle formula specifically the double angle formula for cosine is often combined with the Pythagorean identity. So if you think about putting both of these right next to each other, on the one hand we would have sine squared theta plus cosine squared theta equals 1, and on the other hand we would have cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So what you can do is you could solve for sine squared or solve for cosine squared in terms of cosine of 2 theta and go ahead and plug that back into the top equation. So I'll write down what those identities are when you plug them in, and you could go ahead and work out the details yourself. So you get the following identities. And again, you may want to check the details. Actually, if you take these identities and go even further and solve for cosine of theta or sine of theta by themselves, you get what are known as the half-angle identities for sine and cosine, but I won't be doing all of that. I'll just be listing the following identities. So the idea is really based on combining the double angle identity for cosine with the Pythagorean identity. So the cosine of 2 theta is also 1 minus 2 times the sine squared of theta, and the other is the cosine of 2 theta can be written as 2 cosine squared theta minus 1. So each of those equations you could solve specifically for either sine of theta in equation 1 or cosine theta in equation 2, and solving those yields the double angle identities. Okay, so let's look at a couple examples where we actually verify some trig identities. So one thing when you're verifying a trig identity, what you want to do is you want to work only on one side of the equation if possible. Because when you're verifying an identity, in principle, you don't really want to mess with both sides unless, well, you're trying to verify that they're equal. So if you start messing with both sides, you're kind of asserting the conclusion that these things are equal. So usually if you may kind of need to play around in terms of scratch work to get an idea, but when you write up the final version, you really want to either start on the left-hand side, transform it until you get exactly the right-hand side, or start on the right-hand side and transform that until you get only on the exactly what is shown on the left-hand side. But a lot of the tools that we've just gone over can be used to verify these identities. So example, and we'll just do 2 or 3. Let's say verify each trig identity. So A, let's say we have the sine of theta minus the sine squared of theta, and we want to prove that this is actually in fact the same thing as 1 minus the sine of theta over the cosine of theta. Now, sorry, I meant to write cosecant of theta in the denominator. Excuse me. So there's not necessarily a right answer to the question, which side should I start on? A lot of times it may seem counterintuitive, but you may want to look toward the more complicated side, because usually the more complicated side, there's some things to do, either factor something out or simplify. Whereas if you start on a side of an identity that looks quite simple, there's a number of ways you could complicate it, and it's not so clear which way would be beneficial in the problem necessarily. So in terms of working with these identities, you might say, okay, which side looks more complicated? Or you may just say, well, what could I do? If you look at the right-hand side, it doesn't look like there's maybe any obvious simplifications. But on the left-hand side, at least we could start by factoring. So basically what we want to do here is, let's say, start on the left-hand side and try to transform to the right-hand side. So again, we can start with sine of theta minus sine squared of theta and just factor out the sine of theta. And then we'll have 1 minus the sine of theta. And then, okay, now we notice in parentheses this 1 minus sine of theta matches the top of the numerator of the right-hand side. So how is sine of theta related to the cosecant of theta? Well, we know, so let's say by factoring here, well, so then we're actually done. We can say 1 minus the sine of theta is being divided by the cosecant of theta. And we could say, because since we know that the cosecant of theta is 1 over the sine of theta, then it must also be true that the sine of theta is the reciprocal of the cosecant of theta. So that would be the end of the proof right there. So that was a pretty easy one, in fact. So let's move on to another. How about something like 1 over 1 minus the sine of x plus 1 over 1 plus the sine of x. And we're trying to prove that that's actually, in fact, equal to 2 times the secant square of x. So, again, the right-hand side is pretty simplified. You could maybe turn secant squared x into 1 over cosine squared x, but it's not clear that that will help us. But if we look at the left-hand side, although it looks more complicated, we know that we can get a common denominator. That's a common trick to put fractions together when you have more than one. So let's see how to do that. So let's say start on the left-hand side and get a common denominator. So how do we do that? Well, basically we look at each of the denominators, and we have 1 over 1 minus sine of x plus 1 over 1 plus the sine of x. So each denominator is unique. There's nothing in common. So basically we just want to multiply by 1 plus sine of x over 1 plus sine of x to the first term, and 1 minus sine of x times 1 minus divided by 1 minus sine of x to the second term. Remember, you cannot multiply by something that's not equal to 1 when you're trying to transform an expression. This isn't like we're working on both sides. We're just working on the one side. So we don't want to alter the value of anything. So we have 1 over 1 minus sine of x, and I'm going to multiply it by a clever form of 1 plus the sine of x over 1 plus the sine of x. And the second term, 1 over 1 plus the sine of x, is being multiplied by 1 minus the sine of x over 1 minus the sine of x. Okay, so now we do in fact have a common denominator, so that common denominator is just 1 plus sine of x times 1 minus the sine of x. They both in fact have the same denominator now, and the first fraction has in the numerator 1 plus the sine of x, and the second fraction has in its numerator 1 minus the sine of x. So lo and behold, the positive sine of x and the minus sine of x cancel out, and we're just left with 1 plus 1, so we're left with 2. And then if we FOIL the denominator out, we'll actually just get 1 minus sine squared of x. Well, what is 1 minus sine squared of x? If you think about the Pythagorean identity, we know that sine squared x plus cosine squared x is equal to 1, so 1 minus sine squared of x is just a clever form of the cosine squared of x. So this is by the Pythagorean identity. Right? So in particular, sine squared x plus cosine squared x equals 1. So cosine squared x is 1 minus the sine squared of x. And then lastly, we're trying to show that this is equal to 2 times the secant squared of x. So this is just, we can say this is exactly 2 secant squared of x. Again, this is because secant of x is equal to 1 over the cosine of x. Hence, the 1 over cosine squared x will equal secant squared x. And that's it. So that's the end of our proof. Okay, maybe we'll do one more. So let's look at, let's say, let's try to prove that the cosine of theta divided by 1 minus the sine of theta is equal to secant of theta plus tangent of theta. Now, this one is a little bit trickier. It's not so clear where to go. Again, the right-hand side, we could maybe expand to say, okay, secant theta is 1 over cosine theta, and tangent theta is sine over cosine. So maybe you can put those together. That's one idea. Or you can think about maybe multiplying by the conjugate on the left-hand side. Either idea may work. So sometimes you may try one and it turns out to work, or maybe you hit a dead end and you just restart and try the other method. Or sometimes maybe they both work. Let's go ahead and again start on the left-hand side and multiply by the conjugate. So let's start on the left-hand side and multiply by the conjugate. In particular, the conjugate of the denominator. remember, what does the conjugate mean? Well, if you have some expression a plus b, the conjugate would be a minus b. And the reason that happens is we're going to get a lot of Pythagorean style identities if we do that. So basically what we do is we take cosine of theta over 1 minus the sine of theta, and we're multiplying by the conjugate of the denominator so that it's equivalent to a clever form of 1. So what that looks like is we're multiplying by 1 plus the sine of theta divided by 1 plus the sine of theta. Okay, so to multiply fractions, we just multiply their numerators and multiply their denominators. So we have the cosine of theta times the quantity 1 plus the sine of theta, and in the denominator 1 minus sine of theta times 1 plus sine of theta. And then those things can be combined in the denominator, right? We have the cosine of theta times 1 plus the sine of theta. And the denominator, if you FOIL it out, we get 1 minus the sine squared of theta. So, how does that help us? Well, 1 minus sine squared of theta by the Pythagorean identity is equal to cosine squared theta, similar to how we did that in problem B. So we can replace the denominator now with cosine squared theta by the Pythagorean identity. So now cosine theta over cosine squared theta, we can cancel one factor of cosine theta and write this as 1 over cosine theta divided by the cosine of theta. Oh, sorry, somehow I switched cosine theta to sine theta, or sine theta to cosine theta, so apologies there. Inside the parentheses, we should be having 1 plus sine of theta, not 1 plus cosine of theta. So we're left with the expression 1 plus sine of theta over cosine of theta. So this is just by cancellation of cosine theta. And then our last step, we're just going to split the fraction using the common denominator of cosine theta. And then the very last step is to just use the definition of secant and tangent. So 1 over cosine theta is the secant of theta, and sine of theta over cosine of theta is the tangent of theta, and this is just by definition. So that is the end of the proof. We have reached exactly the right-hand side of the identity. So as you can see, a lot of these different things come up when we're looking at the identities. Usually there's some form of Pythagorean identity in disguise somewhere. But this is Dr. Lennon signing off.